This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Okay, any questions from previous lectures before we start? Oh, good. So this is the last one that I'll do. After this, I think Peter will take over. Today we talk about the metals that you can put in the body. So after polymers and fibers, metals are the most important ones as well. So a lot of the implants, hip implants, dental implants, a lot of them are made of metal. This is the reading pages, and basically when you think of the metal from the very beginning, that you're going to find it's most of the time in the nature, so it has to be, the manufacturers need to do mining and a lot of cleaning to extract the metals from the mines basically, so it's as mineral deposits like ore. So after those refining and extracting the main part that contains the metal, they will make it into basically raw material in bulk form, so it can be bars, it can be sheets and stuff. So they store it there. So from there, the manufacturers of different parts are going to buy it in these forms of stock shapes, which is again sheets, plates, different forms. So when the manufacturer is thinking of designing some parts, they're going to basically buy from the market some sort of shape that's closer to the end design. So for instance, if you want to, if you're a company that wants to build bolts, for example, you're not going to buy any sheets of metals and stuff, so you're going to go for bars, so that's a bit obvious. But knowing which shape is basically the best for the design that you have in the mind is part of the engineering and materials engineering process as well. And then there are different fabrication processes that we'll talk about a little bit, casting, CAD/CAM, grinding and stuff, to make the initial, the basically form of the design, and then there is finishing parts. There's surface preparations, finishing, and a lot of other stuff to go all the way to the final material. Obviously, the fabrication methods depend a lot on the final geometry that you have in mind, and also the forming and machining properties of the metal. So not every metal can be designed in old methods. So some of the, like for instance, titanium is very hard for machining, so they have to come up with other ways of fabrication and stuff. So feasibility, and also if it's worthwhile doing it, the economics is very important. Some methods are investment casting, CAD/CAM, computer-aided design basically, forging, powder metallurgical methods, and grinding and polishing. These are some sorts of fabrication methods that are available out there. So based on the type of the metal, you can choose which one is better. And obviously, each of them is going to give you different material properties that we'll talk about a little bit today. These are some sorts of surface treatment. So once you have built up the bulk of the design, it's very important, as we said, how to treat the surface, because especially for bio purposes, as we are always emphasizing, staying with polymers and textiles and stuff, because the surface is always in contact with the blood and with the body, it's very important to treat that properly, right? So some of the surface modifications are to give you roughness. Some of them is just to coat it, and then chemical binding will happen better. Some of the methods are sintering. So sintering is basically to melt, not to make the metal liquid, but it's sort of intermediate temperature. So it's sort of softens it, and then it will fill up all the holes and stuff on the surface. So that's a way of surface treatment, or plasma flame spray, or flame spraying, that's called. Some of the finishing steps obviously is cleaning, chemical cleaning and passivation, so that the surface doesn't react with parts that you don't want to. This is an example of plasma or thermal spraying. So you see that on the surface there's like this fine, quite rough surface that you have created on the metal. Before going into the rest, I have a quick video to show you some example of the plasma surface treatment.
Thermal spraying process is plasma spraying. Masking defines the areas to be coated, so that the particles to be applied adhere to the component. It is cleaned first. In this surface coating method, powder particles are injected into hot plasma and thereby melted and hit the surface of the component at speeds of up to 450 meters per second. There, they form a material layer that fulfills the requisite characteristics for its function, for example, as wear protection. Online diagnostics ensure that the quality of the results remain at a uniformly high level. Without these surface coatings, modern engines would be unable to supply either the necessary performance over the long term or the necessary service lives.
Yes, you see that as the name plasma brings, it's like they put the powder into this plasma or the very high temperature metal, and then it sprays all around to the surface. So it's very important that you spray it also uniformly to create a good quality surface. So there's other tips and tricks about this when you actually want to do that, and material engineers would study these kind of stuff. The other finishing steps, again, depends on the metal. So ASTM good manufacturing practice would basically provide some standards for different finishing for all sorts of applications and materials. Again, as we said, chemical cleaning and passivation, so using acids and electrolyte would remove a lot of the machining chips and basically clean the surface. And also the chemicals. So, yeah, that's what we talked about. It's very important to take that into account as it's in contact with your blood and the tissue and body. So as an overall thing, that processing, manufacturing, surface modification, all finishing steps is very important. But then again, so there is a relationship obviously between structure and property. So it's important to have what sort of properties are available and then what is required for different applications, as always. This table is giving you the three most common alloys, metal alloys that are available for biomedical and implant purposes. The first one is a stainless steel. Then you have cobalt chromium alloys and titanium alloys. So I guess probably you all heard of titanium alloys. So all the implant parts, the hip implant and everything, dental, most of the time are made from titanium. But then there's also stainless steel parts. So a lot of the fracture fixation parts can be made from any of these basically materials. And then it's giving you actually a summary of the properties and the methods that they have been made. And then this is the ASTM designation. So these are the numbers that the standards is providing, and each of them determines what composition, exactly what percentage of each basically element they've got. And based on those, what sort of properties you're going to get, and it's very important that the manufacturer has actually followed up all these details that are brought about in these standards. Otherwise, you're going to get a faulty, not good quality material. Okay, so the first one is the stainless steel. The most common one is 316L. These are the standard numbers and the grades. So stainless steel is very famous for not for a very low amount of corrosion, especially in vivo. L here stands for low content of carbon, which is very important. So most of the time, carbon is not really desired in the alloys, but it's something that is very plenty of it is in the when they find it in the mine. So it's very important how they have prepared from the very beginning how pure the alloy is. The compositions are mainly iron for stainless steel, but you have 17 to 20% of chromium and 12 to 14% of nickel and some minor amounts of nitrogen, manganese, and sulfur, right? Each of these parts is going to give you different properties to the alloy. So the main building block obviously is iron, which is stainless steel. But then chromium is going to give you corrosion resistance because it forms chromium oxide on the surface, so it will block the surface from getting corroded. But the downside, the disadvantage of a lot of chromium in the structure is actually it's going to give you BCC ferrite phase, which is weaker. Whereas if you add nickel to the structure, it's going to give you FCC austenitic phase. So these are different crystal structures that are very common in the materials. Do you know what they are? BCC, FCC, all sorts of crystal and stuff? You might have had them in at high school. Yeah, so for stainless steel, basically we have very common forms of BCC and FCC. Well, what we mean by that is, so for stainless steel, you mainly have iron, right? In the metals, basically crystal structure, the way they are linked together is very important. So with the BCC, it's called body, I think, center cube, something like that. So what happens here is that the ions are formed like that. So if you have a cube, if I can draw a cube for you. So how many, in this case, the BCC, the FEs are standing in the corners, right? And then there's one right in the middle. That's why it's like body center cube, okay? If I am right, I think. Body center cube. So we have this one, and then there's one in the middle. But then with the FCC, that's, I think, face center cube. In that one, you have a lot more concentration of the Fe. So with the FCC, you have the ions sitting in the faces of the cube, right, as opposed to the corner. Okay, so you will have all the faces. Actually, I think we have both corners of the faces. I'm not sure. You can double check that. We'll show you a much better figure than what I've drawn here. But what happened is the FCC has a lot more concentration, so it's a very dense structure of the crystal as opposed to BCC. So with this one, you will have a lot of empty space, basically, that can be filled sometimes with carbon or a lot of the material that you don't want, or they can slip on each other in the metal. So it's not as strong as FCC, right? So this is a different structure. But interestingly, if you have a BCC structure and then if you add nickel, it's going to have the material to, or stabilize basically the FCC structure, so you will have a stronger crystal basically. That's what happened. So this is happening actually for other metals as well, that the other alloys will have different structures, or the way that the main iron is sitting around the crystal is very important. And then by adding or distracting some other elements, like here, for instance, nickel or other stuff, you can basically stabilize different structure and then get different properties of the material. Some of them are a lot more stronger, some of them are not as much, but some of them are more like brittle, the other ones are more ductile, so you can get different properties in there. So again, you don't want a lot of carbon because it can form carbide into the structure, which can, we have a figure. How can I get rid of this thing? Okay, maybe that's better. Yeah, so if you have a lot of carbide in the, if you look at the microscope, you will have, you will see a lot of grains forming and stuff. And the boundaries are very important because these are the areas of sort of stress concentration, and then where the weaker areas rather than inside the crystal. So if sometimes you have carbides in the, it can actually cause a lot of depletion of the chromium from the boundaries, and then it will give you a weaker material. So this is why different compositions of the material is important in the alloy. So as we said, the desired specification is that you would like to have single-phase austenite or FCC structure as opposed to ferritic or BCC structure here. And obviously you don't want any sulfur going around. It's going to give you the corrosion effect, pitting corrosion is what it's called. The other important factor is that you don't want very large size grains when it's forming. So what's happening is that when you want to fabricate the material, either it's cold working or other techniques, the way, so you have a molten metal, right? And then the way it solidifies into these crystals, into the solid structure is very important to give you a uniform small grain structure, or it's going to give you large size or diameter structures, which is much weaker again, and then you will have a lot of stress concentration and stuff like that. So ASTM actually requires a number of 6, and this is a formula that they have figured out. In here, big N is the number of grains counted in 1 square inch at 100 times magnification. So what they do is they look at the section of a fabricated metal on the microscope, and then they have to count the number that they see within this area, right? And that's, for instance, for N equals 6, this is the size that you will get, 100 microns of grain, each grain, right? And then obviously in this standard they have figured out that what sort of grain size is going to give you what kind of material properties. Tensile properties, compression, failure, fatigue failure, all sorts of mechanical properties that we talked last time as well. This is an example of a cold worked stainless steel, ASTM F138. This is the particular alloy that they can make using cold working, right? So you see a lot of the boundaries of the grains, and then you see some big grains here, and then some, finer areas in there. So as we said, this grain size actually depends on a lot of stuff. So how it is solidified, through what process, is it uniform or not, the annealing cycles, how it's been cooled down from a molten phase, and if it's been recrystallized or whatever has happened to the structure. And why do we care again a lot about the grain size? Here is another relationship that they have figured out. So it's a Hall-Petch type relationship. It's giving you the relationship between the tensile stress, yield stress, and the diameter of the grain. And then you see that if you have a very large grain, you're going to have a weaker material. It's going to break a lot easier. Whereas if you have a more uniform and finer structure, it actually correlates with the yield stress. So this is why it's very important to have that structure. So here's another example. These parts are showing you a lot of plastic deformation. So you see that it's like different grain sizes as well, the boundaries, all sorts of stuff you can see here. So there's a trade-off between what sort of properties you're getting. If you're going to have a lot of plastic deformation, you're going to have ductile material. But if you don't want much plastic deformation or grain size in the crystal, you can get a more brittle material. So again, it depends what you're looking for. Based on that, you will look into different manufacturing processes. Any questions before we get into it? So cobalt chromium is another one that is very common. These are the very common ASTM basically compositions of this alloy that are available, commercially available. As an example here, you have F75 and F799 alloys. They have very similar, basically identical composition, but very different properties. And why is that? They can have totally same composition, but then the way you make it, the way you go from the molten state all the way to the crystal structure, is going to give you very different properties, right? So this one has almost like 70% cobalt. Obviously, it's a cobalt chromium alloy, but then it's got chromium 26 to 30%, and then some nickel as well. The main attribute of the F75 is actually its corrosion resistant, especially in chloride environment, because of the composition that it's got. The surface oxide chromium is going to give you a lot of good resistance into the corrosion as well. And that's why it's used a lot in aerospace and biomedical applications. The way usually it's made is cast by investment casting or lost wax process. Do you know how it is working, this technique? By the name? So it's lost wax. Basically, you have a wax in between that is lost. So it's like you use that wax as a mold in between to build your ceramic mold, and then use the ceramic mold to build or to cast this particular alloy. I've got a video which is a little long, so I'll probably fast forward, but it gives you a bit of a good idea about investment casting. It doesn't have any sound as well. Yeah, so this is the wax that they're putting into this tree thing. That's what they call it. This is the initial mold. So because it's wax and it's easy to work with, it's soft, they can mold it into different shapes. And then once it's complete, it looks like this, but it's obviously soft, so it's not your actual mold. What they do is use this to make the actual mold from ceramic. There you go. So they do different types of coating to just build up the ceramic mold initially. So this is the primary coat that's put in. This part is done manually, but they have to rotate it to get it uniform. It's very important to have a uniform mold. And then after this, they apply another coat to this. And then this is the main part that they're going to make the ceramic from. And here they just use a robot, basically. So it's going to give them a lot more uniform molding. So they put it in there, and then they have a lot of rotation to get the air out, the bubbles out. This is the ceramic mold. Again, this itself has a basically process to give you a good quality mold that doesn't break easily. And you put it in the oven. Here's another layer coat. And then so after the ceramic is formed, now they dewax it. So they take the wax out, basically by melting the wax out of the ceramic. Right. So they put it now in this hot temperature. It's ceramic basically, so it's going to form. So here they have already, so we skipped it, put the molten metal into the ceramic, right? And because obviously this ceramic doesn't melt at that temperature that the metal melts, it's a good one, right? So you can use it for that. So they have already put the molten metal into this. Now they're allowing it to cool down. So this is a part that is very important. So you have a hot molten metal, how it cools down, how slowly or how quickly, it's going to give you very different crystal structure into the final result. Is it already removed? Yeah, so this is the final process to get rid of the extra parts. So you see how this is just using wax initially to make a mold and then use that mold to make this. This is for one way of casting. But what it does is, if you look at this, this is what will happen. If you look at under microscope, you will have a lot of, so these are the grain boundaries. You have a pretty large grain size, and then you have carbides. These are carbides that you have seen under the microscope. And then you see that they're everywhere in the matrix, everywhere in the grain as well. That's going to give the material some weak points, which is not desired. Another thing that happens a lot during casting is dendrite formation. You see this sort of a structure here. So it's not, if you look at this, it's not a very uniform structure that your material has. And obviously it's not going to be very strong. The grain size are about 4 millimeter, which is pretty large, right, compared to the 100 micron that was according to the standard. This is another thing that's happened. So here, there's some defects right in the middle. So what's happening is probably it has started to cool down from the boundaries, obviously. So if you have it in the mold, what happens is that it cools down from the boundaries, and then it forms, as it goes to the middle, it forms some defects. It's not a uniform cooling down and stuff. That's why it's not very desirable or strong. So what happens is that you need to do extra work on it, either cold work or forging or annealing. So heat treatment, that's what very important for this one. This is another one. So you see that there's a lot of porous structure in here. So to come over that, there are other ways instead of casting. One of them is powder metallurgical techniques. So this is going to give you a lot more uniform structure. One example is hot isostatic pressing. A finer powder of the same alloy is actually compacted and sintered together. So they compact it all together and then increase the temperature, but they don't melt it. They increase the temperature almost like halfway to the melting temperature, and then it starts to, so basically what happens is that all these crystals and stuff that you have initially, they start to reform and recrystallize, right? So they will slip into the empty spaces and reform, and then they will become more uniform and denser, basically, and will give you a lot stronger material. So here is a comparison. This is what you had in the F75 with the cast iron. You see much, much larger grains, whereas here you have a lot more uniform and nicer structure. Right? It's the same scale. Any questions? So we're good? Yeah? Clear? So if you want a strong material, would you choose casting or not? Okay, cool. And the last alloy is titanium alloy. This is what you have heard and seen a lot for implants. So the very common types, commercially pure available ones, is F67. And if you compare it with the other ones, with the stainless steel and the chromium, you see that it's got a lot more of the main metal. They usually have like 60–70%. Here we have 98.9 or 99.6% titanium. This is pure titanium, right? There is a little bit of interstitial elements like oxygen, nitrogen, and carbon, and they obviously have very different effects on it. But the other very common one is F136. This one has got extra low interstitial, so this one is very pure, whereas this one has a lot of other elements. And what they do is they will give you different phase stabilizers. So aluminium into this is an alpha phase stabilizer. V is a beta or BCC phase stabilizer, titanium, aluminium. So this is a very common one. So you have a different structure, two different crystal structures in this. Again, this HCP and BCC are very similar to the structures that we talked about here. HCP, I think, is hexagonal, something. Yeah. So it's got more elements of titanium at different locations in the space. So if they're structured differently. So pure titanium is actually made of single alpha microstructure, which is very similar to the BCC. So this is called alpha most of the time. FCC is called gamma. And then we have beta and all sorts of stuff for structures of metals. So if it's like 30% cold work, it's going to give you a grain diameter of about 150 micrometer. And nitrogen, for example, is going to give the material, so if you have a little bit of this in the metal, it's going to give you twice the hardening effect as the other ones, right? The oxygen level is going to also affect the yield strength, tensile, and fatigue strength. So here is an example. These are SN curve, basically, for different composition of the alloys. And you see that the more oxygen you have in the structure, you're going to have stronger fatigue properties, right? So what it does is that it goes into the crystal structure and enhance the fatigue properties of the material. Yep, so we talked about 3 different types of material here. We have alloys, mainly stainless steel, chromium, cobalt chromium, and then you have the titanium. So these ones are going to, based on different manufacturing types, you're going to get different material properties, okay? So if the standard manufacturing process has been followed, you're going to have, okay, so you know that you have this ASTM, blah, 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 you're having this yield strength, fatigue properties, whatever, okay? So this is one part of the story. Here what we have is another story that tells you actually how much the design is important. This is an example of Harrison spinal distraction. So what happens is that the surgeon puts this basically part into the body until the disc fusion is formed, okay? So in this case, what happened is that the surgeon, initially the length of the rod, which is made of stainless steel, was not enough, so they bent it and then put it into the body, okay? And what happened that this rod failed. And then they come in here, the engineers come here and say, okay, what's happened? Was it a weak material that we chose? What was wrong, actually, in this case? When they look at the fracture surface, this is how it looks like, right? So if you look at in here, what do you get from this? What sort of, what do you think has happened that this thing has failed? If you look at this cross-section, actually. So I'm going to block this so you don't do it. So what happened here is that they have bent it, right? So there has been a lot of bending in structure, and then the thing has been moving cyclically a lot. And why do we say that it's been cyclically moving and the failure is because of fatigue and not all of a sudden? If it was like happening all of a sudden for a brittle material, you would have one separation in the entire cross-section, right? If you had it in a plastic thing, you would have a uniform separation of the cross-section and the crystals. What happened here is that it's almost like a beach mark, what you call it. So it's telling you that it's been changing. It's been cyclically changing, and gradually you have different lines here. So gradually separating. So what's happening here is that it's a fatigue failure, right? So this is what very interesting thing happened here. So, and then they realized that, okay, what's happened is that because it was bent, there has been bending, increased bending moment, and then what's happened that in this patient, the spinal fusion didn't form within the time that they expected, and this rod wasn't designed actually for a long duration to take the load for that length of time, and then therefore it failed. So basically what's happening here is that it's telling you that the material has been strong enough for that design, but it hasn't been designed properly, right? So if it wasn't bent and there wasn't much bending or cyclic loading into this, for that compression of tensile strength, it would have been enough, right? Whereas for this particular thing that they didn't predict, it wasn't strong enough in terms of fatigue properties. And they didn't know that because it just simply wasn't designed for this purpose, right? So it's important that you look at the strength, the material that you're choosing, and also look at the design. Any questions for this one? I don't have many more videos. I mean, there's a lot of nice videos if you wanted to ever look at the processing, manufacturing, very different types of casting, so many stuff about surface treatment. They're quite interesting as well if you ever wanted to look at them. But some of them were very long, so I didn't want to bring them to the class. This one is just a very, again, simple thing about machining on the surface of an implant. So this thing has been made already in a lot of surface treatments and stuff, and this is the final finishing, basically, that they're using the machine to treat the surface. Yep, so this is it. If you don't have any questions, that's it for now.
To look for someone as a research assistant. Yeah, I would be interested. Should I send you like my CV or?
Yeah. So, is there a particular area that you're interested in, or you just want to see what's available?
Yeah, I want to see what's available.
Yeah. Okay. Okay.
Should I like send you my CV or should we like meet some?
Oh yeah, definitely. Send me your CV, and then so this week, hopefully next week.
Yeah.
And then also feel free to look at any papers that we have. So I myself work on bone mechanical testing and also a lot of imaging finite element. We have other people in the group as well. Yeah. So Dale, you have met. I don't know if he mentioned anything or if actually maybe he doesn't have much time. He's so I think we will just give you an overview of that.
Yeah, will be great.
Yeah,
Yeah, thank you very much.
No worries.
Thank you.
I'll look first thing when you find out what to join the registry. I'll do that. That's the first step. Yeah, that's the multiple on the directions. Yeah, so we've got to figure out how to join the actually is. So, to do with the central cube, so this is like a model explaining how the electrons and stuff will flow in metal rails or not?
Electrons, not really. So this is not much.
Because the alloys, yeah, so they've got like different metals, different elements inside this cube. So we've got BCC, which is just the generic form of it, isn't it?
No, this is actually, so here we are making
FCC, BCC, and something else as well. There's another one.
Yeah, so that for different metals, there are different
configurations.
Yeah, exactly.
Okay, so
what happens is that, so these are all LEDs.
Yeah, all iron, yeah, they're all iron.
All of them, yeah.
I'm doing this all the way
If you
in
have
first year chemistry, but
Yeah, this is the same. But then if you think of titanium or cobalt,
titanium,
yeah, exactly. So they will sit in their
Different lattices.
things.
Yeah.
Yes,
Okay,
exactly. And then if you look at, there are like quite nice graphs that will give you that based on at different temperature and pressure.
These kind of info dump that we're going to be useful in stuff, choosing our materials and stuff. So
Yeah, well, you
same
probably
profiles,
wouldn't
yeah.
need exactly yourself, but you would. So maybe the more important one is the graph that based on at
Pressure.
each pressure and temperature, what combination of alpha, beta, gamma, whatever
Gives you the best
you have. Then
configuration.
you need to figure out. Yeah. So for instance, if they want to do annealing, they need to know how far they go to, or at what temperature and pressure they keep the metal, and then they start cooling down, heating up, or something like that. Yeah. That's what.
All right.
Yeah.
You also got your email, so
Yeah,
no
sure.
rush in terms of any opportunity or anything that is good, but
Yep. Okay. Yeah. Most likely it would be next week, which I will hopefully be done with my deadline.
don't worry, we're everyone's crazy busy right now. It's that time of the year. Don't worry about it.
Yeah, no problem. Yep.
Don't stress. Insane.
No, that's fine. Thank you.